Next, we're going to talk about continuous random variables and corresponding probability distributions for them. Here are some quick small examples of where continuous random variables exist. So for example, the miles per gallon that a car gets for its gas consumption. So perhaps I go out and fill up the tank of the gas tank of my car, and perhaps from that I realized that I ended up getting 24.1 miles per gallon. Alternatively, maybe it could have been 24.11, maybe 24.1111, maybe 24.12345, and so on. The key is that there's essentially an infinite number of possibilities for the number of miles per gallon that my car gets on a tank of gas. Essentially, the only thing that's limiting us, though, is the amount of precision that we can actually measure the miles per gallon in. Other examples include the amount of precipitation that a city gets per year. Maybe it's 25 inches, maybe it's 25.0134 inches, and so on. Height for people, GPA, the distance for a field goal in football. Maybe it's 34 yards, maybe it's 35 yards, or maybe it's somewhere in between. And essentially, there would be an infinite number of possibilities for the yardage in between 34 and 35. But again, we are often limited by the amount of precision that we use to actually measure it. So, you wouldn't see for a football game 34.3567 yard field goal instead 34 or 35. And so the key is, what I'm trying to get across here is that continuous random variables have an infinite number of possibilities for the values that it can take on within a particular interval, like 34 to 35 yards for a field goal, or maybe 24 to 25 for miles per gallon. And again, the only thing that typically limits our ability to work with these continuous random variables is that the amount of precision that we can actually measure with. In the end, since there's usually so many possibilities of what we can observe, that's fine. And so for that reason, then essentially we have a continuous random variable that we are working with. Now, we're interested in probability distributions. So we're interested in what's the probability, let's say, getting miles per gallon between 25 and 30 for a particular car. And how we work with probability distributions that measure that kind of stuff is very similar to what we saw with discrete random variables, but there are some very important differences that we will talk about. So here's an example. Let's say we're interested in the probability distribution, for GPAs for students at our university or college. And so we're going to let Y be a random variable representing the GPAs for students. And suppose the probability distribution that can characterize all GPAs for all students in our population is this particular function. F of Y is equal to 15 divided by 2048 times Y to the fourth times 4 minus Y. Now, there were particular reasons why I chose this particular probability distribution function, or PDF, and we'll see these as we go along in the semester. And of course, GPAs are between 0 and 4, and we're going to think of this as a continuous random variable, meaning it can be anywhere between 0 and 4. There's essentially an infinite number of possibilities. Of course, you cannot be outside of 0 to 4 for a college GPA, so F of Y is equal to 0 if Y was for some reason outside of that. So in other words, it can't be. Now, again, a capital Y represents a random variable. A lowercase y represents a particular value that it can take on. Let's actually now plot this probability distribution function. And so to do that, I'm going to use a function that we're going to use a lot in R called curve. And to show you how curve works, let me just come over here to R. And let's say I'm interested in the function of f of x is equal to x squared. So just something essentially from what you would learn in an algebra class. So that's the function I'm interested in. And so to plot that function, I'm going to use the curve function. And then the expr argument, which stands for expression, I need to put my mathematical function that I have, put it in the context of x. And since I'm interested in f of x is equal to x squared, I'm going to put in x squared there. Okay, and let's say I want to plot it from, let's say, -1 to +3. So I'm going to create a vector that starts at -1, goes to 3. And that's going to be my xlim argument of curve, similar to what we've seen for xlim of the plot function. I'm going to plot this curve, this function, in red. And let's leave it at that. So when I go ahead and plot it, here's my actual function that's being plotted. It's just f of x is equal to x squared. So for example, when x is 0, f of x, of course, will be 0 squared, or 0. Now let's extend this simple function to this more complicated function that we're plotting for our PDF. Now for us, we're going to have 15 divided by 2048. So we get this part right there. We're going to take it times, and rather than putting y to the 4th, I'm going to put x to the 4th. The reason why I have to put an x there is that this is just how this function works. Whatever goes on the x-axis has to be actually called x. So I'm going to replace the y with x. Take it times 4 minus x. I'm going to plot this, let's say, between 0 and 4, because again, that's where my random variable's defined, essentially. Color red, I'm going to put a nice title on the plot with the main argument. Y-axis label, y-axis is going to have f of y. X-axis label, x-axis is going to have a, is representing y. And LWD corresponds to line width. I'm going to do it twice the normal size, the default of 1. And so you can play around with LWD on your own to see what would happen. And let me go ahead and go over to 10 and run that segment of code so you can see what happens. And there's my plot. Now with these probability distribution functions, just like what we saw with discrete random variables, f of y has to be greater than or equal to 0. So for that particular reason, I'm going to draw a horizontal line on my plot at 0. In other words, f of y is equal to 0. The way I can do that is with what's called the AB line function. The argument h stands for horizontal. Now you might be wondering where does AB line comes from? Well, this function can actually do a number of different things. In particular, what's mainly for is to draw the line y is equal to a plus b times x, where you specify a as the y-intercept, b as the slope. But there's this alternative argument for h that allows me to do horizontal lines. There's also a argument v for vertical lines as well. So let me go ahead and run that and come back to my plot. And there we go. So let me come back over here to Word. Here's the plot again. This is my probability distribution function. Obviously, it looks different from what we've seen before with discrete random variables. But you may remember an example that we looked at with discrete random variables, where we drew a probability histogram. That was for the field goal kicking example. And we found the areas of the bars in that probability histogram. We found that area, and that area equated to probability. Now here with continuous random variables, area underneath this curve that you see between the height of the curve, that red line, to the f of y is equal to 0 horizontal line that we have there, that area corresponds to probability. So for example, if I want to find the probability a student has a GPA between 2.5 and 3.5, I would at least try to draw straight lines there, up from the f of y equals 0 line to the curve that's represented in red. And if I find this area underneath this curve, this is my probability that 2.5 is less than y is less than 3.5. Okay? So, how do we find areas underneath a curve like this? Well, now we can use calculus to do that. So that area there, as we can see, it looks pretty large, maybe about half of the area that we see totally underneath that curve. And so if we simply integrate from from 2.5 to 3.5, my f of y, and I'm going to integrate with respect to y, do all the calculus, I get about 0.56. So the probability a student has a GPA between 2.5 and 3.5 is 0.56. This is how we're going to work with probability distribution functions for continuous random variables. We're going to always try to find areas underneath a curve, such as this. Now, here are some questions. Let me actually do a little bit of erasing first. Oops. Well, unfortunately, my eraser is not working, so I'll just ignore that for now. Or actually, let me see if I can delete it this way. There we go. Okay. So we found the area between 2.5 and 3.5. Well, what happens if we made this range smaller? Let's say between 2.9 and 3.1. So let's go ahead and find the area underneath the curve. And as we can see, this area here is now smaller. So my probability would be smaller. On your own, go through the integration and show it to yourself that indeed this probability is smaller. Now, what if though I made this range here even smaller than what I have on the plot now? Suppose I go from 2.99 to 3.01. And if I could draw a straight line, you could see that area is not even smaller. And suppose I kept on going smaller, 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 to a point where essentially I'm saying, well, what's the probability that 3.0 is less than y is less than 3.0? Or in other words, the probability y is equal to 3.0. Now, as you might imagine, as we can see from this plot, that area is getting smaller and smaller, and eventually it's going to get to a point where the area is 0. So unlike what we had with discrete random variables, where we could write out what's the probability y is equal to a particular number, rather than always going at an interval, here with continuous random variables, this probability of being equal to one particular number is always going to be 0. This is a very important difference between working with continuous random variables and discrete random variables. Please, please make note of that. Now, why does this occur then? Well, think about in terms of calculus what you would be doing here. You're finding the integral from 3.0 to 3.0 f of y dy, where I'm just looking at, of course, where y is defined in terms of this probability distribution function at y equals 3.0. What you will learn in calculus for a simple expression of, let's say if I'm going to integrate from a to a of f of x dx, that was always equal to 0. Same thing occurs here. This also then leads to another important difference between working with continuous random variables and discrete random variables. If I simply found, let's say, f of 3, in other words, y is equal to 3, f of 3, all that's going to give me now, let me do some erasing, all that's going to give me is essentially the height of that curve. That's it. It does not give you a probability itself. So it is not equal to the probability y is equal to 3. It just gives you the height of the curve. Okay. So it's a real brief introduction to working with continuous random variables and their probability distribution functions. Let's look at some characteristics of PDF. So let's say I have a random variable again of y. It has a PDF of f of y. F of y is greater than or equal to 0 for all possible values of y, just like what we saw with discrete random variables. And if I were to integrate from negative infinity to positive infinity of dy of I'm sorry, let me restate that. Integrate from negative infinity to positive infinity of f of y dy. I get 1. What that says is that the area underneath this curve that we just saw here has an area of 1. And remember what we've seen before when we talked about probabilities. If you look at all possible, let's say, events associated with some process or some item, all possible probabilities have to add up to 1. And guess what? All the functions that we're going to have, that we're working with these PDFs for continuous random variables, the area underneath the curve, all the way down to f of y is equal to 0, that area is always going to be equal to 1. So if we liken that or compare this to what we had for a discrete random variable, we would take the sum over all possible values of y, f of y, that would be equal to 1. Essentially, with a continuous random variable, the sum for the discrete is replaced by the integral for the continuous. And if I want to find the probability that y is between some between some interval from a to b, this is where I use integration. Integrate from a to b f of y dy. Now, very frequently, you will hear people call probability distribution functions for continuous random variables. They will often call these as probability density functions. I'm not introducing you to new terminology to confuse you. I'm just telling you this, that sometimes people use this alternative terminology, similar to what we saw for a discrete random variable when we had probability mass functions. Okay. Let's take a look at another example to make sure that we're following this. This deals now with miles per gallon. And let's say that we have a very simple PDF for a continuous random variable x that denotes my miles per gallon for a particular car. F of x is simply just going to be 1/10. For x between 25 and 35, 0 otherwise. Let's take a look at what this PDF looks like then. So between 25 and 35, we have a f of x equal to 1/10. Again, 0 otherwise. So what that means for this particular PDF, which is meant to characterize what's happening in the population of all miles per gallon for a particular type of car, what this is saying is that you cannot have a miles per gallon greater than 35. You cannot have a miles per gallon less than 25. Obviously, it's somewhat unrealistic, but I purposely chose this PDF because it's a simple one so I could demonstrate some concepts. Now, the area underneath this, not exactly a curve, I'm going to call the curve, the area underneath this curve is equal to 1. How would you find that without using calculus? Well, the area of what's a rectangle here, take base times height. So the height is 1/10. The base, it has a length of 10. 10 times 1/10 is 1. Now, let me do some erasing. Now let's say what's the probability that a car gets a miles per gallon between 25 and 30? Again, if I draw a straight line up to the top of the curve and I shade in the area between 25 and 30, that's what the probability is that I'm looking for. As you would imagine, it's going to be 0.5. If I were to use calculus, how would I find that? Well, I take the integral from 25 to 30 of 1/10 dx. Very simple integral. Go through the details on your own, and you get, of course, 0.5. If I were to use then calculus to find the total area underneath that curve, so if I go from negative infinity to positive infinity, what we would do is simply break it up into 3 parts. Negative infinity to 25, f of x we know there is equal to 0. 35 to positive infinity, f of x is equal to 0. So that's why we put a 0 there. And the main thing that we need to do is find the integral from 25 to 35, 1/10 dx. Go through the math again, and you get 1. Okay? So, and I have another example here. Well, what would be the probability x is equal to 30? That probability is equal to 0, and you could go through the math once again through using calculus. Now, the key reason why I'm bringing this up again is notice we have an equality there. So the probability that continuous random variable is ever equal to a particular number is always 0. So what that means then for us when we're working with probabilities, the probability that 25 is less than x is less than 30, for like this example, is equivalent to the probability that x is greater than or equal to 25 and less than 30. It's also equivalent to the probability that x is greater than 25 but less than or equal to 30, and it's equivalent to the probability that 25 is less than or equal to x and x is less than or equal to 30. Okay, so with continuous random variables, it doesn't matter when I'm finding a probability within an interval if I have that equality sign there or not. Now, let's look at it maybe a more realistic way to characterize miles per gallon. I'm going to now use a more complicated probability distribution function that is shown there. This is actually a special kind of probability distribution function. And you're going to see that we have a lot of names for particular PDFs that work well for particular problems. And this is referred to as a normal PDF. And in this particular function, we have pi as in the universal constant 3.14. We also have the exponential function. Again, this comes from your algebra days when you've worked with logarithms. This e is approximately 2.72. Excuse me. And my PDF here is defined between negative infinity and positive infinity in terms of having potentially positive probabilities. Now, of course, you cannot have a negative miles per gallon for a car, but what you'll see very shortly is that that really doesn't come into play for us here. And so if I were to graph this particular PDF, this is what I would get. Ignore the red part for now. The blue part is the actual PDF itself. And so again, area underneath the blue curve there and above the f of x is equal to 0 horizontal line represents probabilities. So we can see that most of the areas between about 22.5 or 23 and 26. So that's what I would expect most of my miles per gallon to be within, because this has all the area underneath the curve essentially. There's very little area underneath that curve once you get greater than 26 or less than 22. And so essentially, then this could also go all the way down to negative infinity, if I could draw a line all the way to negative infinity, and that means a negative miles per gallon. But since that probability would be so small, that's okay. That's why we can still use this probability distribution for this particular case to characterize these miles per gallon. And so if I want to find now the probability, let's say you're between 24 and 25 miles per gallon, again, I find the area underneath the curve. And in fact, for example here, let's say I want to find the probability of having miles per gallon between 25 and 26. That's what corresponds to that red colored in area there underneath that curve. One could again use integration to find that particular probability. But as you can see here, this integral is going to be a lot more difficult to solve than when we were working with f of x is equal to 1/10, or even that GPA example itself. And so because of that, it would be nice if we could have some other way to, let's say, do these integrals for us without us going through and doing everything by hand. And we'll talk about ways to do that later. Okay, let's look at another example dealing with continuous random variables and their corresponding PDFs. This example is called transaction time. Many online commerce websites, or let's say a website like Amazon.com, they're tracking, like how often are they getting, let's say, people to buy stuff. And suppose we let X be a random variable for one of these kinds of cases, for some kind of online retailer. We let X be the number of seconds between transactions. In other words, between people buying stuff. And let's suppose that we can characterize all possible transactions in terms of the time between them by this particular PDF. F of x is equal to 1 over 30 times e raised to the negative x divided by 30 power. Of course, transaction times have to be greater than or equal to 0 seconds. So f of x is equal to this value for x is greater than or equal to 0. Otherwise, f of x is equal to 0 for x less than 0, meaning it can't happen for a transaction time to be less than 0 seconds. So let's go ahead and plot this particular PDF. So what I'm going to do is use my curve function, just similar to what we saw at the beginning of this section. So I'm going to say curve, expr stands for my expression that I'm actually plotting. And then this is where I put my f of x value. It always has to be written in terms of x. exp here corresponds to the exponential function, so that e part there. It's just how you denote it in R. And I'm going to draw the curve from 0 to 140. Now, of course, x can be greater than 140, but through some trial and error, I saw, as you can see in this plot down below, that the line, this red line here, isn't very much above f of x is equal to 0 once you get past 140, so that's why I decided to stop it there. I'm going to draw the line in red, put a y-axis label, and x-axis label. And here's my plot. And so again, area underneath the curve here represents probability. So if I want to find the probability of having a transaction time between 0 and 20 seconds, I would find this area right there. One small note that I want to mention. So right before I use the curve function, I use a function R called par, which stands for graphics parameters. And what this allows you to do is control various aspects of your plot. And I decided to change some of the default aspects to make the plot look just a little bit nicer. And if we go back to one of our earlier plots, okay, what we can see here is that I specify to draw my curve, this is for the GP example, I specify to draw it between 0 and 4. But look what R did. It added a little bit extra room outside of 0 and outside of 4. And this is always done by default. Also, with respect to my y-axis, I only have values that are greater than or equal to 0 and up to about 0.6. And so what R does, it actually goes a little bit further outside of your range of what you're actually plotting. And sometimes, especially when we're drawing PDFs like this, we don't want that to happen. And so I can change the default behavior to remove this extra little room that would always go on these plots by using a par argument called XAXS for x-axis. And then if I use the argument value of I, it then does not extend out the x-axis a little bit further on both sides of what I'm plotting. And I do the same thing with the y-axis. The I stands for internal, meaning what have I internally, let's say, set the limits to be. The default is using R for regular, for lack of a better name. Okay. So again, this PDF here gives us an idea of how much time between people, let's say, buying stuff on a website. Why would this be important to know? Well, you know, these web retailers, they want to have a general sense of, well, what's going on with people buying stuff on their website. So let's say if perhaps, here are two cases where this would be important. Let's say perhaps a web retailer ends up having, let's say, like 1,000 seconds between transactions. And we can see that it would be very unusual to go above 140. And so if you see 1,000 seconds between a transaction, you might be thinking, uh-oh, maybe there's something wrong with the web hosting service. You know, maybe I end up missing some transactions. Alternatively, perhaps the web hosting service has limitations in terms of it can't take too many transactions at approximately exactly the same time. And so if we want to know, well, what's the probability of having, let's say, transactions between 0 and 0.5 seconds, where you might be worried, okay, maybe the server will crash. I can find that probability by finding the area underneath this curve, like that. So those are places where this kind of a PDF will come in handy. And I also have here, are there other examples where this PDF could be useful? Well, yes. This particular PDF, which actually has a special name to it, is called an exponential PDF. That's just the name of the probability distribution function. Obviously, we have the exponential function inside of there too, so that's where the name ends up coming from. But this particular PDF is used often for in engineering for reliability, to understand like how long a part of some machine will last. It's also used in survival analysis too, where you're measuring, let's say, the lifetime of some object or some living thing. Okay, so let's say that I want to find what's the probability that the time between a set of randomly selected consecutive transactions will be longer than 30 seconds. So how do I find that? Well, let's actually go back up to the plot just to emphasize our point here. I need to find the area underneath the curve from 30, which would be right about here, to positive infinity. Okay? So we can see that that probability, that area there, looks pretty substantial. So to find that area underneath the curve, I use calculus. I integrate from 30 to infinity my f of x dx. This is a case, if you remember from your calculus days, and hopefully you do because we'll need to use this, we use u substitution to do this particular integral. And I'll let you go through the details on your own, and one can show that this probability ends up being e to the negative 1, or approximately 0.37. So it matches what we saw in that plot in terms of it was a substantial probability. We could also find the probability of being within an interval itself. So let me go back up to the plot. Sorry to be jumping around here a lot. So I want to find the probability being between 25 and 100. Let me just verify that in my typed or my printed notes. Yep. So I want to find the probability being between here and here. Okay, again, it looks like a pretty substantial probability. How do we find that? Well, we take the integral from 25 to 100 of my f of x dx. And if you go through the math, and the math is shown on page 13, we get 0.3989. Now here's another way that we could find this too. Let me get my eraser. Again, I'm not for sure why I'm having problems with erasing. Okay. So we wanted this area between 25 and 30. What one could also do, and I'm bringing this up because we're going to see this later on, even though it's none of the notes yet. Suppose one wanted to find the probability that y is less than 100. Okay, you would take all this area here. Okay, and also let's look at the probability that, I'm sorry, actually we were working with x. Probability x is less than 25. So here's 25, and so if we could find that area too. And look what happens if you were to subtract these two probabilities. We would get exactly what we wanted to begin with. The probability that x was between 25 and 100. Again, stay tuned for why that's important coming up. Okay. So we have a very important point on caps, highlighted. Here's a very important point. So, we're looking at that transaction example where we were looking at what's the probability a transaction was between, let's say, 25 and 100. Alternatively, what we could think of that probability as is essentially the proportion of transactions in the population that were between 25 and 100. So in this particular case, actually, I was looking at the x greater than 30 example. So the probability that x is greater than 30 can also represent that there are essentially 37% of all times, all transaction times, are more than 30 seconds. So the area underneath that curve represents probability, but you can also think of it as, let's say, the proportion of items in a population that satisfy a certain characteristic, like having transaction time greater than 30. Relate this back to the GPA example as well. So here's where this is a crude drawing of our probability distribution for the GPA example. And if I want to know what's the proportion of the population that has GPAs of, let's say, 2.5 to 4, perhaps, let's say you need a GPA between 2.5 and 4 to graduate. To find that proportion, I would just find the area underneath that curve, which again corresponds to that probability. So a very important point, just to emphasize that, there's a star. Okay. So let's continue. This is on page 14 now. There are ways that we can simulate samples from a population that are characterized by a particular PDF. I'll show you those ways later in our course. But for now, here's an actual sample that I was able to simulate using R. So my data is an example sample.csv. Excuse me. This is a comma delimited file. To read in this file, I use the read.csv function. And just to emphasize how this is done, I'm going to go to that corresponding program. Let's see here. Now, I have a folder on my computer that has this example where is that? Give me a second here. Fortunately, I have so many computer monitors open, it's hard to see where things are at times. And so anyway, so here's this example sample.csv. I need to know what folder that this is located in. So I can come up here to my bar here, and I can see where that folder is. And so if I copy and paste it into my program, and because of R syntax, I need a double backslash between each of the folders on my computer. And again, also just for emphasis, another way that I can find out where that file is actually located on my computer, I can right-click on the file, bring up Properties. Again, they open up in a different computer monitor window. And what I can do is, let's see now, look at Details. And there is the location of that file on my computer. Copy and paste that location into my R program. And so if I use read.csv with that, put into an object called set1 for the lack of a better name, this is what I get. I read it in. Now it's ready to go in R. So if I use the head function with set1, we can see we have observation number, and X then represents these actual transaction times. So 8.78 here represents 8.78 seconds between, or for that first transaction. And then between the first and the second transaction, there was 2.8 seconds, and so on. I can use the tail function to look at the last few observations in my data set. So the last one was 52 seconds. Okay, let me come back over here to Word. So this is an actual sample. This sample comes from a population that's characterized by this PDF that we've seen. So with that then, well, what proportion of these times would you expect to be greater than 30? In other words, we're essentially saying, let's have our sample estimate the probability that X is greater than 30. Since this is an estimate, I'm going to put a little hat on top of that probability statement. And so before we found the probability that X was greater than 30, we found that to be 0.37 approximately. So we would expect from the sample that we just have of 1,000 transaction times, we would expect about 37% of them to be greater than 30. Similarly, what proportion of these times would you expect to be between 25 and 100? Again, we found this to be approximately 0.3989 before from our PDF, so our sample should be approximately around that. So let's let R now, with this sample, actually check what is the proportion between these particular values, what's the proportion that's greater than 30. So to do this then, the first thing I'm going to do is just get an object that has my sample size in it. I could say n gets 1,000, or I could say, okay, let's find the length of all the items that are in my X variable. Put that into an object called n, and I get 1,000. Then, let's take a look at this. Actually, let me come over here to 10. Make sure I have that run. Okay, so I want to do a comparison. I want to compare each of these transaction times that's in the X part of set 1. I want to compare it to 30. And I want to see, is a particular transaction time greater than 30 or not? So if I execute this particular code here, look what happens. I get a bunch of trues and falses. So R is actually doing a logical comparison for each item in that what ends up being actually a vector. And so if I just look at the head of it, and let's compare that to the head of set 1, we can see that first transaction time is not greater than 30, so that's why we have a false. The second transaction time is not greater than 30, so we have a false there. But that third transaction time of 71.2 seconds is greater than 30, so that's why we have a true there. And so now I want to find out how many of them actually were greater than 30. So I want to do some math with trues and falses. And the way that R operates here is that it will automatically convert a true to a 1 and a false to 0. So if I use the function sum for sum up everything that's in that object, I get 377. And if I take that 377 divided by n, 0.377, let's come back here. So what this is telling me is that 37.7% of the items in the sample were greater than 30. What did we expect? About 0.37. Okay, so we're getting what we would expect. Now, since all these comparisons here, which gives us ones and zeros or trues and falses, since the numerical form is a 1 or a 0, if I were to simply take the mean of all those ones and zeros, I get the equivalent of summing and then dividing by n. So 3.377. Well, what proportion are between 25 and 100? Well, I can again look at all the values of my sample. Are they greater than 25? I can also look at all the values of my sample. Are they less than 100? And then if I use an ampersand to join these two things together, this is R's equivalent of and. So I need both of these things to actually hold true for a true to be returned. And if I take the mean of all these trues and falses, the mean of all the corresponding ones and zeros, I get 0.412. Let's compare that to what we would expect, 0.3989. So again, this sample comes from a population that's characterized by this PDF. And by looking at this sample, we can hopefully get a better understanding what these PDFs represent. They're representing how items are distributed in a population. And then we can use this PDF to our advantage to find corresponding probabilities. Okay. Some notes, some questions. Suppose another sample is taken of size 1,000. Would you expect the same proportions that we just saw here? Well, the answer is no, because it's going to be a different sample. There's going to be variability from one sample to the next. So one shouldn't necessarily expect that. But again, we should expect something similar to what this PDF is giving us. Suppose a larger sample was taken. What would you expect to occur with these proportions relative to the probabilities? Well, think about it this way, and this goes back to our original GPA example that we saw at the very beginning of the semester. The larger my sample is, the more representative it is going to be of the population. So generally speaking, as I take a sample maybe of 10,000, 100,000, 1,000,000 transaction times, I would expect, generally speaking, these proportions that I just calculated before to get closer to what the PDF is telling me should happen. Conversely, think about what would happen if I took a smaller sample. What would happen to these probabilities that we're calculating, or these proportions for this sample? What would you expect to have happen to those relative to the PDF? If you're not for sure what the answer is, please ask. So let's look at a histogram so we can see a picture of what this sample is given us. So we've seen how to do histograms before. We have the hist function. And I'm going to do a histogram of all my transaction times. And what we see here is a general shape to the histogram that's very, very similar to what we saw when we actually drew the PDF itself. Let's just go back to that just to emphasize this. Of course, I have so much writing there, it's hard to see. There's my PDF. It's the same general shape. So, again, this helps us illustrate then what it means to have a PDF that represents what's happening in a population, and then what will happen with the corresponding sample. And what one could do is actually find then the frequency distribution, the relative frequency distribution of this sample as well, just like what we've done earlier in our course. Excuse me. So since we've done it earlier in our course, I'm not going to go through all the details, but please make sure you go through these details on your own. And so on that histogram itself, that first bar represents transaction times between 0 and 20 seconds. There were 480 out of 1,000 that fit within that. That means our relative frequency was 0.48. For between 20 and 40, there was 256 transaction times. This has a relative frequency of 0.26. And so if we look at the cumulative relative frequency, this 0.74 there is 0.48 plus 0.26. Okay. So we saw that the histogram had the same general shape as what our PDF did. It would be nice if we could actually, let's say, overlay the two. And in fact, we can. All we need to do, excuse me, is just change the y-axis scale for that histogram so we can plot the PDF in its original y-axis scale on top of it. R does this automatically for us by, in the hist function itself, if we add an argument called freq equal true is the default, meaning it's going to plot the frequency for each category. If we instead change that to false, it's going to rescale the y-axis of that histogram so it's on exactly the same scale as if I wanted to plot the PDF. You're not required to know exactly how that is done. If you want to know a little bit more information, here's some of the details we can ask during our class too. And so to do this plot, I'm going to do basically exactly the same before. Use the hist function, add that freq equal false argument. I'm going to change my y-axis limits here just to make sure I get as high as I want to on the y-axis rather than going with the default. And then what I can do is use the curve function to plot my PDF. I do it exactly the same as before, but now I put add equal true there, meaning I want to add it to my current plot that's being opened. And in case I didn't mention this before, the way that the curve function works is it's going to, by default, find 101 values of x between the smallest x value and the largest x value that you're interested in, and actually evaluate whatever you put in for the expr function. It's going to plot all those 101 values and draw a line to connect those 101 values. Depending upon the shape of the actual function you're drawing, sometimes it's nicer to have a finer grid of points to evaluate your expression at. And so in this particular case, I put 1,000. And so here's our plot. And we can see that indeed our histogram follows exactly the same shape as what our PDF does. Okay, let's see now. So we have some notes here. Some more notes about, well, what if you had a smaller sample size or a larger sample size? What would you expect this histogram to look like relative to the actual PDF? Well, the larger your sample size is, the closer the the closer the histogram should be in terms of following what the PDF is giving you. For a smaller sample size, well, you're going to see more variability from one sample to the next. So the histogram should be in a same general shape, but you would see more differences because that sample is not going to be as representative of the population itself, since it's a smaller sample. And here's a very good problem, or a very good note or question. For a general data problem outside of this example, how could one check if a PDF is appropriate for a particular data setting? Well, take a sample, do a histogram, plot the PDF. If the histogram follows the same general shape as a PDF, great. That means that that sample can be characterized by that particular PDF. If, however, there's big differences, and let's say if I also had some bars that look like this on this histogram, obviously that PDF does not follow the same shape as a histogram. So would I want to use this PDF then to model what's actually happening in a particular real sense for, if this was for transaction times? Well, no. And so what we often do in statistics is that we have a PDF, such as what we just saw earlier, and then we think that works. And what we do is we try to verify it by taking a sample, getting a histogram, compare that histogram to the PDF. If they match up, great. If they don't match up, then maybe you need some other kind of PDF to model this real-life situation. Okay, so let's take a look at another example. Let's find the time between transactions such that 95% are less than this value. In other words, I want to find the 95th percentile relative to this PDF, or equivalently, you could think of it as the 0.95 quantile. In a calculus sense, then, what does this mean? I want to find some number, let's call it C for the lack of a better letter, some number C such that 0.95 is equal to the probability x is less than C. In other words, let's integrate from 0 to C my f of x dx. So if I go through the math, I see that I get 1 minus e raised to the negative c divided by 30 power. But this time, I know what's on the left-hand side here. It's 0.95. And so now I can just solve for c. If I do that, I get c is equal to 30 times log of 20, where log means natural log. Typically in statistics, we mostly just work with natural log. So because of that, whenever you see a log in statistics, it's usually almost always a natural log. So c is equal to 30 times the log of 20, or approximately 89.87. So again, let's go back to our plot and see if this makes sense. Okay, so 89 is approximately right about here. And what we're saying is that the area to the left of 89 is about 0.95. Yeah, this makes sense relative to our plot. So you would expect then, again, most transaction times, 95% of them, to be less than about 89 seconds. I should say time between transactions, that is. Another example, suppose you wanted to find the time between transactions such that 5% are less than this particular value. In other words, find the 0.05 quantile. And you go through a very similar process. I'm going to integrate from 0 to c, where I'm looking for this number c, and I get 1.54 approximately. Well, let's compare that with what we got in our sample. And if you remember from earlier in our course, we can use the quantile function to find quantiles, to find percentiles, where the key thing is that we put in our data into the x argument. And then for the probs argument, this is where we put in, well, which percentile or quantile you actually want. So for 0.05, I observe 1.57 as my quantile. For 0.95, I observe 78.49. So this matches pretty well with that. We see the 78.49 is a little bit off, though, from 89.87. You might be wondering, well, geez, that seems more off than I would like. But here's the reason why this occurs. Kind of an interesting reason. So here's my PDF, not drawn to scale. We have about 89s right about there. So here's about 140 that we saw in our plot. And we can see that there's not going to be a whole lot of information available to us in our sample way out on the far right-hand side of the distribution because there's a little probability, there's a little area out there. So that means I'm not going to observe many values out there. And so because of that, then, if I'm not observing much information that far out, it's going to be harder to get a good estimate for what that quantile would be. As opposed to when we were looking for that 0.05 quantile, we can see that we're going to have a lot of observations that are less than 1.54 seconds. And so because of that, that's why I had a lot of information to draw from, and that's why that estimate seems to be pretty good compared to what the PDF is telling me. If you have more questions about that, please let me know. Okay. Now, when we were working with discrete random variables, we defined something called cumulative distribution function, which just accumulated probabilities as y got larger. Well, we can do a similar thing here now with a continuous random variable. So with the discrete random variable, this is what we have. We are just simply adding up these probabilities as a function of y. Now, our CDF, capital F of y, and that should be a lowercase y there. Sorry about that. We have capital F of y it just is representing the probability my random variable y is less than little y, a particular value of y. And that's just going to be the integral from negative infinity to y, f of t dt. Now, why am I using a t in here rather than a y? It's because I don't want you to mix up the limits of integration with what I'm integrating over. So, wherever you saw y and f of y before, just replace it with a t, that's fine, and then do your integral that way. Okay, so that's what my CDF, that's how you find it. And again, what we can see is as y is increasing, it's accumulating probabilities. It's going to accumulate area underneath the curve. So if we go back to this particular drawing as we had before, this is for my transaction times. So maybe I have a y here. Find capital F of y for that. And then let's say I move y out here. Now I'm going to take what I had before and add some more stuff to it, or add more area. So that's why I'm accumulating probabilities. So let's actually find then the CDF for the transaction time example. So capital F of x, in other words, the probability my random variable x is less than a particular value that it can take on little x. I'm going to integrate from 0 to x of 1 over 30 times e raised to the negative t divided by 30 power dt. Go through the math, you get 1 minus e raised to the negative x divided by 30 power. Remember that x is x is defined from 0 to infinity. So I have that there. Little or capital F of x is equal to 0 when x is less than 0, of course, because you can't have probabilities down there. So let's actually do a plot. So again, I use my curve function for my exp argument. I put in what my CDF is, and this is what it looks like. Always with a CDF, you're going to keep on getting larger and larger and larger in terms of that y-axis because you're accumulating probabilities. So if we look at x equals 0, the first possible value that x can have with a positive probability essentially, we can see that, and this should be capital F of x, sorry about that. We can see that, well, we're starting at 0. And then as x is increasing, my cumulative probabilities are increasing as well until we get to a point where f of x is going to be equal to approximately 1. That's my CDF. Now, where can this be useful? Well, what we were often finding was probabilities like x is greater than 30 or x is less than 30, stuff like that. Let's take the case of probability x is less than 75. Well, what I can do is I can come back to my plot here, find 75, draw a line up to the curve, and then go over, and that's going to correspond to 0.9179. So in other words, this plot gives you probabilities for x being less than a particular number. So probability x is less than 75 is equal to my capital F, my CDF, evaluated at 75, or in other words, 1 minus e to the negative 75 power divided by 30. Do the math, you get 0.9179. Going the other direction, probability x is greater than 75. Now I use my complement. So remember how we had the probability of A is equal to 1 minus the probability of A complement. So the probability x is greater than 75 is equal to 1 minus the probability x is less than 75. And again, I don't need to worry about putting an equal sign in there because I'm working with continuous random variables. So this probability then is equivalent to 1 minus my CDF evaluated at 75, or in other words, 0.0821. So again, these CDFs give you a convenient way to essentially avoid integration if you already have the CDF to work with. One small note here. Now, when we were working with the PDF, area underneath the curve corresponded to probability. That is not the case here with CDFs. So I am not looking for this area here. I am not. doing that. Again, I am not doing that. The reason why I emphasize that is sometimes students get that mixed up. Rather, all I'm doing is I'm going on my CDF curve. I'm finding where my x is. I project up to where it hits the curve. And I come over, and now there's my probability that I'm looking at. Here's another place where we use these CDFs. Suppose I'm interested in the probability that x is between 25 and 30. Well, of course, I could do the integration to find that. But instead, what I can do, and this corresponds to something I mentioned earlier, is I can break this probability up. Look at the probability x is less than 30 minus the probability x is less than 25. So let's go back to my curve originally. I think this will be good enough. So let's see, 25 is right about there. 30 is right about there. So if I project up, probability x is less than 25 would be this area right here. Probability x is greater than 30. I'm sorry, is less than 30. Probability x is less than 30 would be this probability. And if you subtract the two, what are you left with? The area that's in between. That area is equivalent to the CDF evaluated at 30 minus the CDF evaluated at 25. So CDFs can be very useful to find probabilities like this. We will be doing this kind of stuff essentially for the rest of the semesters. That's why this is important. And if you do have questions about it, you do need to ask so we can get that understanding down now. On your own, I won't ask you a question about this, but on your own, you should go back to your old calculus book and compare this statement here that we just showed to the fundamental theorem of calculus. That's typically in every calculus book out there. And basically what we're doing here is applying the fundamental theorem of calculus. Okay, so now with the CDF here, you might be wondering, okay, could I use a sample to estimate the CDF? And the answer is yes. Similar to how we had a histogram help us estimate the shape of the PDF, or give us an idea if the PDF matches what's happening with the sample. We can do exactly the same thing with a CDF. Okay, so we're going to, the estimated CDF is typically referred to as the Empirical Cdf, or Ecdf. And basically what it's plotting is the cumulative relative frequency for a sample. That's it. Here's a mathematical expression for it. Let's actually look at an easier to look at mathematical expression. So if I want to know, well, what is my empirical CDF? So notice how I have a hat on top of the capital F to represent an estimate, to differentiate from the regular capital F. If I want to find my empirical CDF, evaluate a particular value of y, let's say like 25 for that transaction time example, all I would need to do is find the number of my observations. So I have, let's say, n possible observations. Find the number of observations that are less or equal to 25, divided by the total number of observations that exists in my sample, and what I get here is a proportion. How often did I have a transaction time less than 25? This is an informal expression for the Ecdf. Another example. Let's say I'm interested in little y equal to 5. So in other words, capital F of y is equal to the number of transactions with less than or equal to 5 seconds, all over the 1,000 different transaction times that we observed in our sample. That's all that an empirical CDF is. And so you can find this for any possible value of y of interest. A more formal representation is what looks like this here. What we have inside this sum is what's called an indicator function. We often use these in statistics to indicate if something occurs or not. If the stuff that's inside the indicator function is true, you get a 1. If it's false, you get a 0. So in our particular case, for our transaction times, y sub 1 was 8.78. And let's say I want, again, capital F hat of y of 5. Okay. Now, to find that with this particular equation here, I have a sample size of 1,000. I'm going to take it times a sum. And this sum corresponds to y1 is less than 5. The indicator function y1 is less than 5, plus the indicator function y2 is less than 5, plus I'm going to go all the way up to the 1,000th one is less than 5. And so with y1 equal to 8.78, is 8.78 less than 5? No. So this will be a 0. Now, y2, my sample, and you can actually go back to the sample to actually see this. I've actually just written it down. y2 is equal to 2.81. So is 2.81 less than 5? Yes, it is. So this becomes a 1. And we do that for all 1,000 values in our sample. We add them up, divide by 1,000, and that's how you get your proportion of observations that are less than 5. Less or equal to 5. This is a more mathematical way to represent this. If you're more comfortable with how I represented it here, that's fine. Okay, so let's take a look at an example that illustrates this. So previously, we've looked at how we could find a frequency distribution corresponding to our transaction times. So if you remember, we had 480 that were between 0 and 20 seconds. Here's my cumulative relative frequency, my relative frequency as well. So the number of transaction times that are less or equal to 40 seconds is 0.74, or the proportions is 0.74. So what an empirical CDF then essentially does, it finds this frequency distribution, relative frequency, or I'm sorry, the cumulative relative frequency distribution, but now for any possible value of y. And so there's a function R called Ecdf that automatically essentially finds that for us. So there's one argument, x, and I put in what my times were. And so that if I were to now use the resulting object called f dot hat, and let's say f, and actually I've got examples down here. And if I say f dot hat of 10, I get back what the cumulative, what the Ecdf would be, 0.262. So there were 26.2% of my observations that were less than 20 in my, less than 10 in my sample. F dot hat of 300 is equal to 1, meaning all my observations were less than 1. And I think I failed to mention this. What this Ecdf function gives you is actually it creates its own function, and I call it f dot hat, which then allows me to find my Ecdf. On your own, take a look at this example here, where I look at a sequence of numbers from 20 to 220 by 20, and I find, well, what would be the Ecdf value for that? And if we come back up here, let me remove the break, you're going to see all these proportions corresponding to what we had for previously when we found the frequency distribution and the relative frequency distribution. Okay, so let's actually do a plot. So to do a plot of the Ecdf, I can use the plot.ecdf function. I put in my data. I'm going to have a line width thickness of twice the default. I'm going to put some grid lines on the plot. So I'm going to use the argument panel.first is equal to grid, y-axis label, x-axis label. I'm going to make then the Ecdf blue, and I don't need a title on this plot. And so let me actually go over here to tend to do that. And here's my Ecdf. Now, what this ends up actually looking like is very similar to the step function that we saw earlier with discrete random variables when we had a CDF plot for them. And what this is representing is, again, let's say if I'm at x equals 50, if I start at 50, if you see where my mouse is, and I project up and I go over, about 82% of my observations were less than or equal to 50. Now let's actually now plot my CDF on top of it. And so to do that, I'm going to include the add equal true argument, but everything else is going to remain the same from what I did before. And there we go. The red line represents the actual CDF itself, and we can see the Ecdf follows the same shape as the CDF. And this again helps you see, well, what does it mean to have a sample characterized by a particular probability distribution function? We saw that with respect to a histogram and a PDF. This is the equivalent, the Ecdf compared to the CDF. I can also add a nice little legend to the plot as well to differentiate the CDF from the Ecdf. So if I say, I'm going to put the legend at x equal 100 relative to the x-axis, y-axis 0.6. What am I going to put in there for the legend? Well, I'm going to put in two text descriptors, my Ecdf, my CDF. Line type equal 1 corresponds to a solid line. My Ecdf was in blue, my CDF was in red, my line width was 2, and BTY equal n. You don't have to use it, I like to use it. BTY stands for box type. Do I want a box around my legend? I said no. That's what the n corresponds to. And here we go. And now we have a nice legend that's added to the plot. Okay. So we saw how to get the CDF from the PDF, but let's say you had the CDF instead. Could you get the PDF? And the answer is yes. You just go in the opposite direction. So before we went to get from the PDF to the CDF, we use integration. Now to get from the CDF to the PDF, excuse me, we use a derivative. So if I take the derivative of my CDF with respect to y, I get little f of y back my PDF. Just to show you how that works, here's my transaction time example once again. Here's my CDF. When I take the derivative of 1 minus e to the negative x divided by 30, use just regular stuff that you would learn in calculus, and I get exactly what I would have before. And so lastly, we have this example dealing with wind speed in Lincoln, Nebraska. I'm not going to go through all the statistics, the mathematical details here, because sometimes I work with this data for projects or homework assignments for students. But the purpose here is to show you an example, a real life example where PDFs can work pretty good. And so let's let y be the wind speed for a particular day. Excuse me. Now you can actually get this information off the web, and you get per day wind speed. Now obviously wind speeds change throughout the day, and to be honest, I'm not for sure exactly what they use for the daily wind speed. You know, perhaps we think of it as maybe, let's say, the wind speed at noon, okay? Or it could be, let's say, an average wind speed throughout the day. We won't ignore that. We'll just say we have one wind speed per day. And a PDF that often works very well with wind speeds in Lincoln, Nebraska, for these actually are February wind speeds, is this PDF right here. And we can see, excuse me, this is a lot more complicated PDF than what we've seen previously. Again, y represents the wind speed. We have, again, the exponential function in there. But we also have some Greek letters. So we have a gamma, we have a beta, we have a delta, and there are multiple places there. What you will see in this during this semester, this gamma, this beta, and this delta are actually population parameters. Similar to how we saw, let's say, mu was a population parameter before. Here, these are other kinds of parameters, and what they are going to do is control the shape of the PDF in terms of, if you think of it in terms of it being plotted. And for different values of delta, different values of gamma, different values of beta, we can get, let's say, a better fit for what the PDF plot will look like in comparison to the histogram itself. And this actual PDF here corresponds to what's called a Weibull distribution, a commonly used probability distribution in a variety of different places. And through methods that we'll talk about later in this course, we can find what the best values for these parameters will be. And so if we take these best values and we plot the PDF with it, put it on top of the histogram, we can see that generally speaking, this histogram is following a very similar shape to what the PDF is. And that's why we can now use this PDF to model what these wind speeds would be. Where would this be of interest? Well, for example, with wind turbines. Electric companies want to understand for particular locations where they put turbines, they want to understand how windy it is. What's the distribution of the winds? Because then they can equate that to the amount of electricity that will be generated. So what these electric companies can do is that they can take samples of wind speeds at particular locations across the state, across the country, and they can come up with a probability distribution that best fits what's actually happening in that sample, and then use that probability distribution function to get an idea of, eventually, through some more calculations, how much electricity they will be able to generate. Okay, to end with here, we have one last question, and that is, can f of y be greater than 1 for a continuous random variable, capital Y? I want you to think about that and realize that what happens with discrete random variables is not always the same as with continuous random variables. Think about it. If you have questions, let me know, and we'll talk about it. So with that, then that this concludes this particular section on continuous random variables and their corresponding probability distribution functions.